Hi everyone, I hope it's going well. This is lesson 4 of our third unit. Today we're going to talk about dependent and independent events, and we've actually been talking about this without naming them already a bit in this unit, but we'll kind of expand on that as we go through. So a couple things. One, we talked about compound events, and that's really just where you have multiple events combined together. And if you do, then you're obviously going to multiply those probabilities together. So what we're going to tack onto this is the difference between independent and dependent events. So an independent event, for example, in this situation, a coin is flipped 4 times and it turns up heads each time. What's the probability that the 5th trial will also be heads? And sometimes people think, even though you're on a streak of some sort, the probability is not changing each time I flip this coin. So the probability remains a half. It's not going to change. This is an example of where you have independent probability. And what that means is that one event is not impacting the occurrence of the next event. The probability remains constant, or in different situations, it's just not going to change. So, for example, we've seen spinning a spinner, rolling a die, drawing a card from a deck in the keywords here with replacement. So if I put it back, then it remains independent. Or if you roll one die twice, the probability is not going to change. And that means that you just simply take those probabilities of A and B and you multiply them together if you have multiple events. So remember this, that represents this upside down U thing, really represents and. So the probability of A and B just means, and if you add another C, you would multiply by C. Down here, we saw something like this before. What's the probability that when you toss a coin 3 times, you land a head 2 times and then a tail? So in that specific order. And so really, it's just the probability of each event. So 2 heads, 1 tail. And the probability of each of those is simple. It's just 1/2, and I'm multiplying them together. And so each time I roll or toss the coin, rather, I'm just multiplying by another 1/2. So I get 1 out of 8. So let's try one where it kind of is different probabilities, so it's not always going to be the same. It says Katerina estimates the probability of passing the math test is 0.9, and the probability of her winning her volleyball game is 0.8. Find the probability that she will both pass and win volleyball. So we're doing both together. It's both have to occur. So probability of pass and win. So in this, because they are independent events, I can just take the probability of passing times the probability of winning. And so we got 0.9 times my 0.8 for winning, and you get 0.72. You can set this up in a tree diagram, and I'm just going to show this to the side because sometimes it is helpful. So the first event in this case would be whether or not she passes her math test or she fails it. So there's event 1. And in this situation, you've got 0.9 for pass, which only leaves 0.1 or 10% for failing. So there's my first event. The second event, you could win the volleyball game or you lose. And that's going to be in both parts here. And my probability of winning is 0.8. My probability of losing is 0.2, like that. So there are 4 different situations that could happen, right? Pass win, pass lose, or fail win, or fail lose. So what we just looked at was the probability of passing, so the 0.9 times the probability of winning. In the next question, where it's like, what's the probability that she passes math but loses volleyball? Even though it's really pass and lose. And so when we think of losing here, we first have to recognize the probability of losing is really the complement. And I put this already over on the tree diagram. So 1 minus the probability of winning, so 0.2. So we need that. So overall, the probability of passing and losing. So I've got 0.9. I don't always need to write out what these represent as long as they're the right numbers. It's good. So I've got 0.9 times 0.2, which gives me 0.18. Then the last one here is what's the probability of having at least one success? So we'll say success is like she wins or she passes. So in this scenario, because it's at least one, she could just, and I'm going to highlight these, pass and lose, or pass and win. That would be when she has two successes. Or she could technically fail and also win. So there are three situations where this can happen. If you do that, it's totally fine if you take the long way, and I'll show that here in a second. But it's easier to think of the complement. So if it's at least one success, the complement would be 1 minus the probability that there is no success. And no success really is represented by failing and losing. So this scenario would be 1 minus the probability of failing times the probability of losing. So if I put that in, I've got 1 minus failing would be 0.1, losing is 0.2, and we get 1 minus 0.02. So that's a bit more efficient than taking the longer way, and I'll just pop this into our note here. And if you go the long way, you still get the same answer because everything is just simply adding up to 1. But this is what it would look like. You could go all three of those scenarios, pass, lose, fail, win, pass, win, and do all of those calculations as a separate thing. And obviously that's a lot more work than just doing the complement, which is 1 minus the probability of no success. So both ways work. Obviously one is quicker and easier than the other. Okay, so the next thing I want to talk about is just the opposite of independent events, which is obviously dependent events. And sometimes once you know more information in a situation or more information is provided, the probability of an event will increase or decrease depending on the situation. So in those situations, you know that you're going to have dependent probability because the probability is changing. So this is often things like our classic one is dealing cards without replacement. And things like weather, like once more information is known, like if it's cloudy, there's a greater chance of rain. If the pressure increases, there's a greater chance of sun. There's lots of things where that comes out. But this one, the cards without replacement, really just means that your probability is going to change each time you deal another card. But we're going to look at a specific situation which involves Venn diagrams like we did last class. So if we look at this Venn diagram to the side here, it says this Venn diagram shows the number of students in a class who study Italian and French. So we've got a number of people in each. So suppose a student is randomly selected from the class and we find out a piece of information. We find out that the student studies French. So this is where you have this conditional kind of aspect to this, which is like a known condition. It's a known piece of information which is going to impact the probability of anything going further when we talk about that student. So it says we can determine the probability that this student also studies Italian, and this is called conditional probability because it is the probability of studying Italian occurring on the fact or condition that I know that they already are a person who studies French. So let's break this down. If you look at this, there is some new notation. The probability of studying Italian given that French has occurred would look like this. The probability of I, and then we've talked about this a little bit, but that just like in grade 11 functions, when you're talking about domain and range, you write this line to represent the given. So this is like the given information or such that French has occurred. And if I look at the Venn diagram, so the first thing I know is that this person that we're looking at studies French. So this is the given condition. And when you think about it this way, it helps to kind of understand it a bit better. I know that the person studies French, but what's the probability that they also study Italian? And so when I think of this, I'm really just looking at this bubble because these are the only people that study French. So hence, that's the given condition. So when I write this out, if I want the probability that that person studies Italian, I'm really just looking at, well, how many people study Italian in here? And that's going to be this number, which is the overlap between Italian and French. So I have 8 out of the total number of people within the given condition, which is 8 plus 7, those people who study French. So I end up with 8 out of 15. There's another way to write this with a formula which will also work, and it looks a little like this, and we'll go through this a bit more later, but if I have the probability of I given F, it becomes the probability of the intersection divided by the probability of the given condition. And this will always work out. So if I think of, first I kind of need the total of everything, but the probability of I and F, so that's this 8 thing. But the probability should be out of the total number of people. And so my total, I need to add up all of the numbers within my Venn diagram. So I've got 14 plus 8 plus 7. And then I've also have this plus 1. And so that comes out to a total of 30 people. So my probability of Italian and French is 8 out of 30. And my probability of French, if I look at the French speakers or people who are studying French, I've got 15 out of 30. And what happens here is that you just work this out, the 30s are going to cancel, and you're left with just the same thing we had to the left, which is 8 out of 15. So this is an example where you have conditional probability, and you can actually work out that formula just like I had above, but generalize it a bit more. And so there's this multiplication rule for conditional probability. And if you know that there's something where you have one new condition that's known, the probability of events A and B occurring looks a little different than what we saw above when they were independent. It really just becomes the probability of A, right? But it's times the probability now that B is given A. And so what that means is like B has been impacted by the probability of A. And this is a formula that will be given to you. And you can rearrange it if you need to in order to find, let's say I wanted the probability of B given A. It's simply going to be rearranged where I divide by the probability of A. And so I have A intersect B over the probability of A. So another version of this formula that can be quite useful. So this is the same, it's just rearranged. Okay, let's try one, and if you want, you can try this on your own, but I'm going to create the Venn diagram to help this. So if you want to, pause right now, or you can try it out. So it says, in a class of 25 students, 14 like pizza and 16 like iced coffee. 1 student likes neither, and 6 students like both. 1 student is randomly selected from the class. What's the probability that the student likes pizza? So the first one, hopefully this one's easy. If I look at the probability of just liking pizza, it doesn't say that they can't like both, it's just who likes pizza. So we've got 14 people like pizza, and we've got 25 students in the class, so this is just going to be 14 out of 25, really easy. The second part, B, is the probability that the student likes pizza given that he or she likes iced coffee. So this is that conditional aspect given. So we know that the person already likes iced coffee. So I'm going to approach it in 2 ways. One is to use the Venn diagram. So let's create the Venn diagram. So I know that there is an intersection because they tell us that. And we start with that intersection. So one student likes neither. I could throw that out here. There's a 1. 6 students like both. So put that in the intersection. Let's say this is pizza and this is iced coffee, IC. So my pizza, there are 14 total. So this is 14 minus 6. So I get 8 people who just like pizza. And then similar on the other side, I have 16 who like iced coffee, so that leaves 10 here. So if I use the kind of approach that I did on the previous one, I want the probability that they like pizza given they like iced coffee. So I have to go to this part. If they like iced coffee, I'm only thinking of these people. So that's really the given condition. And if I do that, then it's, well, what's the probability that someone likes pizza in this group? And if you work it out, you've got 6 people of those who like pizza out of the total in that group being 16. And so this just becomes 3/8, which is perfectly good answer. We use the Venn diagram. If you use the formula, pizza given iced coffee, then I've got the probability of pizza intersect iced coffee over the given condition, the probability of the given condition, so iced coffee, like that. And now you can just take the numbers as they're given. So the probability of pizza and iced coffee would be 6 out of my total number of people, which is 25. And the probability of iced coffee, which is, in this case, what did we say? We had 16 out of 25. And what will happen is always these things are going to cancel, the denominators of both, and you end up with 6 out of 16, which can be simplified into just 3 out of 8. Same answer as above. Those are good to practice, and I do recommend you try it with the Venn diagram. I think it's helpful to think it through like that. Okay, one more example here, and then you can try the homework below and in the textbook. It says the probability that Eva will go to Western is 1/5. So she got a 20% chance, she thinks. So subjective probability. The probability that she will go to another university is 50% or 1/2. Jack is considering going to Western, but it is conditional on Eva also going. So they've thrown this word in there to help, I think. It says he estimates that the conditional probability is 3/4, but what's the probability that both Eva and Jack go to Western? So there's a lot of information here, and let's kind of break it down and separate it out. So I'm going to start here with the conditional probability. Let's say A is, Eva goes to Western. So we have 2 situations. And B can be Jack going to Western. Those are our 2 situations. The probability of Eva going, we're told, is 1/5. And the other part to this is this conditional probability, which they're saying the probability that Jack goes to Western is based on if she goes. So probability of B given A is equal to this 3/4. And what they're asking for in this scenario, what's the probability that Jack, both Eva and Jack, will go to Western? And if you think of that in the notation, this is the probability of A and B. Both are going to go. And so this is my and part. Both things are happening. So if you use the formula from above, that's this first version, the probability of A and B. It's the probability of A times the probability of B given A. So I've got probability of A and B probability of A times the probability of B given A. And we have both those pieces of information. So we've got 1/5 times 3/4, which just becomes 3 out of 20, or if you wanted it as a decimal, 0.15. So if you can kind of work out what each thing represents, there is some extraneous information here, and that's that the probability that she will go to another university is 1/2. We really didn't need that. I'm just going to cross it out. We didn't need that piece of information. It's just kind of there to throw us off. Okay, if you have any questions, just let me know. But the homework here, I want you to try these questions down below, and I would start with those. And then you can go to the textbook questions listed here. Okay. Talk to you soon. Bye.